everybody to this to the second day of this workshop. So we have today two sessions as yesterday. So we have the first part, 4 talks, and 3 talks in the second half of today. So we have some small announcements to make. So there is a document, a Google Doc, for you to suggest the topics to discuss in tomorrow's panel at the end of the workshop. So please send us your suggestions. There is a second announcement that the local organizers would like for the speakers to send their slides before or after your talk. So to make those slides online. And just a reminder that this meeting is being recorded. So the first speaker today is Denny Lee from Databricks, who will address a topic of analyzing LSST data with Apache Spark. So Denny, the floor is yours.
Perfect. Thank you very much for the wonderful introduction. So in this case, it's actually going to be 2 of us. It'll be myself and Colin Slater from University of Washington to talk about optimizing LSST analysis with Apache Spark. I'm going to start off a little bit on the Apache Spark side of the house, and then Colin will go ahead and respond on specifically on LSST, and then we'll still leave a little bit of time for some questions. So next slide, please. So first things first, I wanted to call out that if you want to learn more about Apache Spark, there actually is a free ebook, Learning Spark 2nd edition. I happen to be one of the co-authors of it, and we'll make sure to include the slides so that way you don't have to look for it. But basically, if you want to know more about Apache Spark, Delta Lake, MLflow, Qualys, these are all open source projects. You can go ahead and get the ebook for free by going to this link. Okay, but again, we'll give you the slides, so no problem. Go ahead, next slide, please. Oh, just go directly, finish the slide, sorry, Colin. Yes, so just a little tiny bit about, one more slide, sorry, Colin. A little bit about Databricks. We're a unified data analytics platform for data science, data engineering, and business analytics. We are the original creators of these popular open source projects. All right, that's it. We can skip that. Now, the real meat of the session. What is Spark, or what is Apache Spark? Next slide, sorry. So from a long story short, basically Apache Spark is an engine that allows you to do many different diverse workloads in many different diverse environments. It's an open source project. It's pretty much at this point, it's sort of become one of the de facto engines when it comes to big data processing. On top of the core of a set of standard libraries, you have the ability to run Spark SQL, which allows you to write SQL statements, streaming to do streaming analytics, machine learning with MLlib, and calculations. We're using GraphX or graph frames, actually. It's scale out and fault tolerant, and you can use Python, Java, Scala, and R APIs as well. And on below those standard libraries, you can use lots of different services, whether it's Hadoop, Cassandra, OpenStack, Mesos, Google Compute Engine, things of that nature. So it allows you to use one single processing engine framework across multiple environments. Next slide, please. And it's part of the very much part of the open source ecosystem. So without listing all the different data sources and environments and applications, many systems can basically interoperate with Apache Spark. So one person could be running on Windows, another person could be running on Mac, one could be working on the cloud or on-prem. It doesn't really matter, right? Apache Spark actually works across multiple environments. It's an in-memory compute engine to process lots of data. And so whether you're, in fact, many people, customers, community members, what they do is they actually have very diverse environments. So parts of their systems are on-premise within their own data centers. Part of it's actually in the cloud. It's okay. They use Apache Spark, so that way they have the same processing framework across the entire environment. Next slide, please. And just to overemphasize that point, whether it's Databricks, the company that I work for, or whether you're running on Azure or AWS or Cloudera on-prem, or Alibaba or Google Cloud, doesn't matter. The environments actually work perfectly fine. Next slide, please. So what can Spark do? That's the real meat of it. Next slide. I'm going to give you the slides because there's a lot to go through in a short amount of time. But for example, you have examples of like big telecoms, like South Korean telecom, that want to do real-time network analysis. This is actually from about 5 or 6 years ago, so it's actually significantly larger now. But they're basically building a network enterprise data warehouse to do real-time analytics of their base stations. So they're doing stream processing, plus running SQL queries, plus running fast queries on large data sets, right? So pretty cool scenario. Next slide, please. How about machine learning? So these are just some of the highlights of machine learning. So with Spark MLlib, you can use machine learning to use data to identify patterns, make decisions. The core value is of machine learning, of course, is automated decision making, and this is especially helpful when at least when you're working with Apache Spark, to do this when you're dealing with terabytes, hundreds of terabytes or petabytes of data. Many use cases, including marketing and advertising optimization, security monitoring, fraud detection, operations optimization. There are many more of the cases, but these are just some of the highlights. So next slide, please. And then same context was in streaming. So we have another link inside here that talks about various use cases, streaming ETL, triggers, data enrichment, things of that nature. So the context basically, now that I'm almost finished my part, and we'll switch over to Colin to talk about a specific use case, is that Apache Spark itself actually covers a lot of different use cases. So if you haven't already worked with it, highly recommend you trying it out. You can go to Databricks. There's Databricks-try, which allows you to go ahead and try it out for free. But then you can also go to the Apache Spark download and download it for free and run it on your own environment as well. All right, so saying that, I'm done with my little section. Let's switch over to Colin. Colin, you can go ahead and talk a little bit specifically about LSST and AXS.
Excellent. Okay, so you got the quick high-level overview of what Spark does. Now I'm going to bring it back to the astronomical context. There we go. Okay. So I guess I should sort of talk first about how does that Spark relate to the topic of this meeting. And I think the big way is that we know that some of the upcoming surveys are really exceeding the capabilities of our sort of big single machine databases. And we know we need to move to distributed solutions. And we also know that the questions that our users want to ask about these upcoming surveys are more complicated than they have been in the past. And so the users are also looking for distributed solutions to doing their computation on our data. And so at UW, we've used Spark as a good tool to understand kind of both sides of this problem. So it lets us explore kind of the data center questions, like how do we store data so that it's efficient for answering astronomical questions? How do we scale storage and compute? How do we manage it? At the same time, we have to ask the kind of complementary question of like, well, how are users going to ask their questions about the data? How do they write queries that deal with this complicated data model that now has light curves and other features? And so what we've done is we've taken Spark as kind of our base layer, and then we've built a set of extensions on top of Spark that sort of meet those astronomy specific needs. So we call this the astronomy extensions for Spark. Some of that is optimization. So for particular types of queries like spatial cross matches, where it's like the day-to-day thing in astronomy, we've modified Spark's query engine to optimize that type of query, particularly in a distributed environment where the data are stored potentially elsewhere from where the computation is being done. We've also added kind of astronomy convenience functions on top, so like that the users see words that they're familiar with, like cross-match in the API. And we also implement our own choices about storage and partitioning that are kind of embedded in the code so that the users can kind of bring their data to the system, and then the system partitions and stores that in a way that supports this optimized access. So for the user's perspective, I think the key functionality, a lot of this is what Denny said, that like they get full SQL capabilities if it's on their local machine or distributed. It's all driven by Jupyter. So they're able to, from within the Jupyter notebook, do the full cycle of query, download, plot, and then iterate on that. And then they have the full Python capabilities. So just to give a few highlights, very brief highlights of results. So we've been running billion object scale cross matches on kind of interactive minute-ish timescales. This is something like ZTF to pan-stars or pan-stars to Ys. These are all billion object catalogs. This is really taking advantage of that, those query optimizations that you can find a lot more details about in that archive link. And this is running both locally and on AWS, where the storage is separate from the compute nodes, and it still runs efficiently on these fast timescales. The other highlight is that we've had real users who've been doing their time series analysis on the ZTF data using the system. So we have a group of users who are interested in finding objects where the object dims for a while and then it comes back up to sort of the normal brightness a few days later. And so they were able to write and test a little piece of Python that looks at a light curve and says, does this meet my criteria? And then test that locally on a copy of the data that we had. Just sort of on one big machine. It's easy for testing. They can do whatever they like to see if it works. But then once they had that kernel figured out and they kind of debugged it, they were able to scale that up to ZTF just by copying that notebook to our instance on Amazon, where we could scale up to about 100 EC2 nodes and do the entire search over every single light curve in ZTF in about 2 or 3 hours instead of them coming back a few days later. So that's something that's being in the process of being written up, and hopefully we'll have a paper out on that soon. So okay, those are the super fast highlights. I'll just conclude to say that we've been testing distributed query processing and distributed user computation with Spark on real data with ZTF. You can find links to the papers and to the code. We also have test instances that we're happy to connect people with so they can try it out on their own. So that's all I have. Thanks.
Thanks, Colin, and thanks, Denny. I don't see any question on the Google Doc that we are using for questions, so I am going to have one. What is your feeling, at least, or your experience regarding the scalability of the Spark solution for data sets the size of LSST, for instance, that we are working on? So do you feel Spark will be a solution for analyzing data at the scale the LSST needs?
I guess I'll give my quick perspective, which is that I think Spark's the scalability is the thing that Spark is the best at. So the bigger the data, the more Spark provides value for analyzing that data.
Yes, and just to add to Colin's perspective, that's exactly right. I mean, Spark was very much designed for petabyte scales. And so it's not to say that you can't use it for terabytes or gigabytes. You absolutely can, but it's extremely well designed for the purpose of massively large scale. That the context is about distributing your data across multiple nodes and being somewhat efficient about it. If we had a little bit more time, we could even dive into the latest releases of Spark 3.0, which actually includes ability to handle skewed data and things of that nature. So there's a very large community that actually keeps on pushing Spark forward for the open source community to make sure that it can process much larger amounts of data.
Thanks. There is a question from Vandana. Can you comment on the compatibility of Parquet with IVOA registry and TAP?
Yeah, so we have a kind of an ongoing project to try and get Spark to speak natively to the TAP interface. So we still need Spark in between Parquet and that TAP layer. I've never thought about kind of going directly to Parquet. These are things that are kind of on our mind, but we haven't finished any work on this yet. Is that kind of addressing the question, I hope?
I hope so. I have another one from Julia. So could you expand a little bit on the optimized data partition used by AXS? Is it compatible with commonly used partitioning based on Hill Peaks pixels? So compatibility with Hill Peaks.
So the full details are in the paper, and I think it's a sort of complicated thing to describe, but the quick answer is that it's very different than Hill Peaks, because what we have are lots of very thin, long partitions in DEC. So it's sort of more like the zones partitioning. And then you can read through those individual long partitions in a very orderly manner without having to create sort of the tree structure that you would need in order to do cross-matching with Hill pixels. So it's quite a different strategy than Hill pixels.
Okay, so we will find that information in the paper. There is a last question from Jorge. How many users are really developing in Spark? How do you help them in cases necessary?
Oh, sure, I can probably take that. So there are actually hundreds upon thousands of contributors to Apache Spark. If you go to the GitHub page, for example, there's currently about 1,600 contributors across hundreds of different companies. So in terms of the community helping each other out, definitely join our Apache Spark distribution lists. Just go to spark.apache.org. Where you'll be able to find them, and that and Stack Overflow. We're extremely active in those arenas, and of course on GitHub itself. So if you have questions directly there, you want to create an issue, we're pretty active on that as well. So hopefully that helps you answer your question as well.
Okay, thank you. So there are additional questions. I invite speakers to look at the Slack or the Google Doc to answer, because otherwise we will be late. So thanks again, Denny and Colin, for your talk. So our second speaker today, we are changing continent, is Chenzhou Cui from the National Astronomical Observatories in China. Chenzhou, this is the floor is yours.
Yeah. Hello, everyone. Can you see my screen?
Yes, now it is full screen, so this is perfect.
Yeah, okay, thank you. First, congratulations on the 10th anniversary for the LIneA for the library. And I'm happy here to give a talk about the IVOA and the Chinese Virtual Observatory. And my title, my talk title is Towards an Astronomical Science Platform. And I gave the talk on behalf of the China team, and with contributions from the IVOA, the International Virtual Observatory Alliance. So, as we all know, astronomy now is a data-driven science. About 20 years ago, yeah, it means around the 2000 years, astronomy stepped into terabytes area, driven by several sky survey products. For example, the 2DF, Galaxy Redshift Survey, the SDSS, and in China, we have a large-scale spectrum sky survey product named LAMOST. and we have the Gaia, and then about 10 to 12 years ago, the astronomy stepped into the paradise, and now we are stepping to the EB area, driven by several new generation astronomical products, including the FAST, the 500 diameter radio telescope in China, the SK, the Rubin Observatory LSST product, and the Euclid from ESA, from the European community. So astronomy is entering a new area of big data, and where the data size are too large to download as before and analyze using users' own facilities. So we have to change to satisfy the new requirements from our astronomers, from our users. The idea of virtual observatory was initiated about 20 years ago. The vision of the VO, we know the web is transparent. So the goal of the virtual observatory is to achieve the same feeling for astronomical data, and we hope it is all available to explore in a single transparent system. And we hope astronomical data science and tools and services should work seamlessly together. And the VO allows astronomers to interrogate multiple data centers in a seamless and transparent way, and provides new powerful analysis and realization tools within that system, and gives data centers a standard framework for publishing and delivering services using their data. So we often say, like the World Wide Web, the virtual observatory is not a fixed system, but rather a way of doing things. Here in blue, I give one sentence of my definition for virtual observatory. I define it as a data-intensively online astronomical research and education environments, taking advantages of advanced information technologies to achieve seamless global access to astronomical information. To improve the virtual observatory developments and the implementation globally. So in 2002, the International Virtual Observatory Alliance was created. The IVOA is an organization that debates and agrees the technical standards that are needed to make the VO possible, and a focal point for VO aspirations, and a framework for discussing and sharing VO ideas and technology. Currently, the IVOA, the Alliance, consists of 21 member VO projects. And you see on the right hand, it is a group photo for the VO projects logos. And there are more national communities show their interest to join the IVOA. For example, Netherlands and Thailand. And for the IVOA community, we have currently 6 working groups and 8 interest groups. The main difference between the working groups and the interest groups are working groups is the main focus of working groups is to define standards and protocols for interoperability of astronomical data. While the interest groups is just acting as a bridge between the VO community and the astronomer community to collect scientific requirements from our scientific users. Each year, the IVOA will organize 2 interoperability meetings. The first is in May, and the second usually in October or November, together with IDAS meeting. Since the creation of IVOA, currently the islands, the working groups and interest groups have been defined about 46 interoperability standards. Here, there are some applications for the IVOA interoperability applications and services. Maybe quite a part of us have used these tools, including Aladdin from CDAC, the TopCat, spectral tools for WhaleSpec from Whale Spanish, the notebook, and many other tools. And here, there are also some more online systems and services. For example, the ESO Science Portal, the Worldwide Telescope from AAS, the Firefly from Caltech, and the ESA Sky Portal, and the gravitational wavelength portal, and the CDAC services, and the Spanish whale field profile services. And of course, there are many other online services and systems provided by the whale members. During the last several years, a very popular idea was created by scientific data community, that is FIRE. FIRE means fundable, accessible, interoperable, and reusable. Since the beginning of the virtual observatory, WHALE shares the same principle for the current share. And we provided the registry to fund the resources globally, and through the data access protocol to provide access services for resources, and through the WHALE cross standards and the protocols, we make the resources required by astronomical research interoperable. So WHALE is a FIRE platform, and the different WHALE products provided online WHALE data services and tools laid a solid groundwork for the science platform idea. Why we need science platform in astronomy, and we know the development of astronomical data will increase greatly in the near future. And since platforms are being developed to allow researchers to efficiently analyze big data science, and since these science platforms will enable analyze close to the data and support online data mining and machine learning, you don't need to download data to your local environments and facilities. And of course, in the near future, limited by the bandwidth globally, it is almost impossible for you to download data worldwide. Here, I listed several examples for astronomical science platforms, including the Chinese Virtual Observatory, the ICI, the Science Server, the CANFAR from CADC, the NOAO Data Lab. And I know yesterday, for example, LSST had already introduced CNES server and his latest thinkings about the data science. And most science platforms in astronomy employ a similar architecture and technologies to provide an interactive data analysis environments. Based on a cloud computing platform, just mentioned by our last speaker, for example, the Amazon Cloud, the Alibaba Cloud, and we're using Jupyter Hub and with Jupyter Lab used as an interface for exploratory data mining and analysis. And the interactive environment is generally deployed using container techniques, mainly for the Docker technology. Here are some more details in introduction about several examples. Here I listed several of them. For example, the NOAO Data Lab. The Astro Data Lab is operated by the NOAO and the National Center for Ground-Based Nighttime Astronomy in the US. And the Data Lab platform provided large catalogs, pixel data services, virtual storage and visualization, computing processing, and access to published data sets, data publication, and exportable workflows and distributed software services. Another example is CANFAR. CANFAR means Canada Advanced Network for Astronomical Research. Yeah, it is a very popular science platform for astronomers now. So how to create a basic source detection pipeline on CANFAR virtual machine, it will go over from here. It is an example how to use the CANFAR system. The CANFAR system provided users, including storage management, group management, data publication, batch processing, OpenStack cloud services, cloud migration, and the classic CADC astronomical data search services. And here we also have JJ from CADC. And so this CANFAR provided a very usable platform for the astronomical research now. The next example is from the Johns Hopkins University. This platform was originated from the SDSS Sky Server system. This one, the principal investigator is Alice Zale. And this platform also provided the hosted data sets, computer images, science research environments, education, and wealthy help documents for the end users. In the last part, I will give a more detailed introduction about the Chinese Virtual Observatory, or another name is the National Astronomical Data Centre. The NADC was announced by Chinese government in June 2019 as one of the first 20 national scientific data centers. Well, the NADC has a long history, more than 30 years. The NADC was the first acting as the WDC, World Data Center System Astronomy, and created in 1989. So currently we have formed a whole life cycle management platform for astronomical data. From the CADC, or Chinese Virtual Observatory websites, we can find several channels. The first one is observation channel. we provide call for proposal and online peer review, proposals management, observation plans services for the telescope management teams. And the second one is the data discovery and access, based on virtual observatory protocols and standardizations. We provided the VO data search and data access services for the end users. And the next one is cloud computing. Cloud computing means we provided the computing and analyzing services and environments for data processing and data mining. And additionally, we also provided paper data and cloud-based storage services to the users. The next channel from the channel wheel is public and citizen science channel. You know, the VO linking a large number of data sets globally. The astronomical data or big data from astronomy are not only valuable resources for astronomical research, at the same time, they are very valuable resources for education and public outreach. So the China will put a lot of efforts for the education and the citizen science projects. Here, for the long-term data curation and available data services from the platform, we are facing two kinds of groups. So first is the project data. Project data means from telescope projects, especially sky survey, and we have planned archiving systems proposal on archiving plans and provided quality control for the archiving data sets and release and open access plans. And I know many of us know the the open access or release plan from the SDSS. So this project data is similar as the SDSS data release plan. And additionally, we also provided the user contributed data, especially the paper data and the user driven submission. You can submit your data sets to the system and provide metadata information for your data sets. So the data center or the portal, the online system will provide you with persistent access services. Here is an example from the China WO. This is data release services for LSST. LSST is a large-scale area, multi-fiber spectrum sky survey telescope from China. And now the total number of spectrum obtained by the telescope has been over 100 million. It is the largest spectrum data size in the world. The China WO provided more than 20 data releases to Chinese users and global users. Here, taking advantages of the WO technologies, we provided the online visualization, online analyzing, and the different download methods for the users. Yeah. So and currently the scientific paper results published from the LSST data size has over 700 papers. Another example from the China WO Science platform is the FAST. FAST is a 500-meter aperture spherical radio telescope located in a karst depression in Guizhou in southwest of China. Is the world's largest single dish radio telescope with a receiving area equivalent to 30 football fields. And it is practiced that FAST will maintain its world-class status for the next 20 to 30 years. Just 2 weeks ago, the FAST telescope is open to the world, and the call for proposal is just underway. So all the astronomers, especially radio astronomers, are very welcome to submit their proposals. The China VO provided the call for proposal and the online peer review, data management, and the data release for the largest radio telescope. Yeah, another service from the China VO platform is paper data. Paper data is a long-term storage and open access service for also paper data. For example, if you submit a paper to a journal, and you can upload or storage your related data and software and maybe videos and large images to the paper data services. The paper data service will provide you stable storage, a long-term accessible URL, and we also provide you a DOI. And now the China VO paper data has been recognized as a persistent repository by the AAS journals. So there are already tens of scientific data papers submitted or archived their related data to this storage service. So all of you are welcome to archive or submit storage your paper related data to this platform, and we will provide you a stable and professional service. In the end, there are some challenges and future trends for astronomical science platform. From my personal opinion, a very big challenge for the science platform is a single sign-on or interconnection among different science platforms. And we know we have already several running science platform, but we have, all of us have their own user systems and authentication and authorization systems. So how to realize a single sign-on? It is a big challenge because there are many other related problems for this solution or for this hope. At the same time, there are some trends for science platforms, and we know that we have been in the area of hybrid networks. We are using internet, mobile internet, satellite internet, and the 5G and maybe 6G in the near future. So how to integrate all these different kinds of networks together? It will be an important trend for the science platform in the future. And the next one is really big data. Really big data, that means the time domain astronomy and the multi-messenger astronomy are hot topics and research fields for astronomy. With these scientific drivers, the data amount is increasing very fast. So also the bandwidth of our networks is also increasing, but it will be more and more difficult or almost impossible for you to transfer a large data set from one place to another one, or from the remote server to your local facilities. So the scientific platforms will be crucial for our future astronomy research. And we must, depending on these online research platforms in the future. The next trend is artificial intelligence. And we know AI get more and more achievements during the last several years. And so astronomers should take full advantages of these progresses and achievements from other fields and industries, and taking full advantages of the data mining and machine learning for our astronomical research. The last one, but not least, is citizen science. I mentioned before, astronomical data is also a very valuable resource for education, for the public, and for our students. So an astronomical science platform should be facing to professional astronomers, and at the same time, we will provide services and resources to our public users and citizens. And we will provide inclusion, diversity, and equity for the whole community. So this is my my talk. And now the VO-based science platform is just from an idea to a research mode for our astronomers, for our astronomical community. Thank you for, if you are interested in my talk, you can get more information from my scientific data. This is my paper. This is a special paper for the science platform issue published in astronomy and computing. Thank you.
Thanks, Chenzhou, for this presentation. Especially it is late in Beijing for you, so thanks for that. So we have time for one question by Robert Nikute. In fact, there are three questions. So the first one: does the China VO science platform run on Alibaba Cloud or on your own hardware?
Our platform is using the mixed cloud computing system. We're using Alibaba Cloud and our own cloud computing facilities at the same time.
Second question: how many users does it have?
It is a very good question. From the portal, you can get the registered users currently is more than 24,000. However, most of them are public users, and about 3,000 to 4,000 professional astronomers.
And the third question is it open to the international astronomy community or only to researchers in China?
This is a global platform, and everyone can register and use resources there.
Okay, thanks again. And please don't forget to send your slides to the organizers so that people can get your contact information.
Okay, so, thank you.
Thanks, Chenzhou. So our next speaker is JJ Kavelaars. I hope I am pronouncing correctly your name. Sorry if that was the case. From the Canadian Astronomy Data Centre. So the floor is yours, JJ. You can start sharing, and we have now your full slides on full screen. So please go ahead.
Great, thanks very much. Yeah, so I'm from the Canadian Astronomy Data Centre, and we are the sort of maintainers of something called the Canadian Advanced Network for Astronomy Research, or CANFAR. And I'm just going to sort of walk you through a little bit of how CANFAR got to be what it is now. So start with where's my mouse going? There we go. So there we go. So first I want to just highlight the partners that we're working with. So this is the group of supporters, basically the sponsors for the CANFAR platform. CADC contributes in kind through funding from the National Research Council of Canada. And we received a fair bit of support initially and ongoing from CANARY, which is the network platform, the network organization in Canada. And CANARY saw basically that there was a need to kind of expand the way scientists were using the network for research purposes, where they were, actually connecting through to the compute and running on platforms as opposed to just sending email to each other, basically. So the Canadian Space Agency has been a longtime supporter of the CADC and has recently been supporting our efforts on science platforms. We use Compute Canada as our cloud provider for the CANFAR platform. And very recently, NRAO funded a development study through the ALMA development study program, which expanded some of the capacities of the CANFAR platform. So the CADC itself, just as a kind of like, let you all know about it a little bit. So in 2019, we had about 1.7 petabytes of data stored within the CADC. It's 300-ish million files. That's data that comes from about 200 different telescope instrument combinations that are searchable and retrievable from within the CADC. So it's a pretty broad range of data collections, quite diverse. The map here shows you basically where on the sky the data holdings from the CADC are coming from. And in 2019, we delivered about a petabyte of the archive out to users over the internet. And that's a success and a failure, because basically it means that we pushed a petabyte of data out over the internet. Maybe what scientists really wanted was to be able to analyze a petabyte of data. They didn't necessarily want to have to transfer it to their home institutions. And we have about 10,000 users, where users are basically IP addresses, because most of the data is open and we don't really track who's taking data from us. So this is well known to this community, but I just want to remind you that archives increase science productivity. They're critical really to the science productivity piece. This is from the annual report of the Canada-France-Hawaii telescope that just came out. And they have a plot here of the rate of publications coming from the facility, which is, there's always this upward trend in science productivity. Everybody shows this as a really important part of their funding case. What's interesting is, is the green line here for us, this is the archival. This is people who retrieve data from the archive, which is the CADC is the primary archive for CFHT. And it makes up roughly a third of all the science publications that come out of the facility. Another third comes from people taking catalogs that are, I think, basically published mostly through Vizier and publishing papers on those. And then another third from newly acquired data in that year. So I want to tell the story here of the development of CANFAR, and I'm going to use the CFHT legacy surveys and the CFHT data system as kind of the motivator for all of this. So in 2003, CFHT switched operational modes to start running in surveys. And so they started with something they called the legacy survey. And the CFHT legacy surveys were producing these 100 gigabyte a night data sets, which in 2003 was an insurmountable challenge for local computing and network capacities. The majority of the calibration across this, use of this camera is a wide field imaging camera. The majority of calibration is going to be uniform across all different science programs. So there was a need to basically uniformly calibrate the data and send that to the users. And then the computing model available at the national facilities didn't really map well onto the map reduced kind of concept, where you would farm out many jobs onto various machines, and they would all do the same processing and then send the data back, which is how you would calibrate. If you have 40 CCDs in this mosaic, you could have 40 threads going, and each one doing a different part, and so on. So what we looked at was, how can we improve the infrastructure basically to make this general computing that's needed for all these projects kind of uniform. So within the CADC, we built a grid engine system. We ran this from 2003 to 2009. This was internal to our computing center with a Sun grid engine system set up to calibrate and stack these imaging data. External to us, the CFHT Supernova Legacy Survey team was funded to build their own compute center, which was a very small compute center by today's standards, but at the time was pretty substantial for their needs. And one of the issues they ran into was sustainability, where they got a grant, they built the compute system, they hired sysadmins, they hired some developers. But as SNLS, the Supernova Legacy Survey, started to wrap up, the ability to attract funding into that to continue to support that was difficult. And CFHT was providing the corrected for instrumental signatures, and then CADC was providing these calibrated and stacked images to the whole science community, except to the Supernova Legacy Survey team, who were using their own kind of pipeline. One of the main problems we ran into with this was this kind of last mile problem, where users would try to retrieve data from the CADC and they would be pulling 100 gigabytes to their local computer at home, and it was very slow for them. And another issue that we kept running into was our members list. So the way we were maintaining access was we had basically a text file, right, in an HT access file in a directory, and we just kept adding names to it. And taking names out based on what the director of the telescope told us to do. And it was a really clunky way of maintaining access to such a high value data set. So there were those kind of problems were starting to emerge in this model. So to overcome the large data set problem, because we created stacks, what we built was an image cutout service. So most of the images are empty, so they're not interesting to the astronomer. You're really interested in the part of the image that has data. Most of the spectrum, if you're doing spectra stuff, is continuum, so it's really probably not that interesting either. Most of the time series are uniform, so most of the time series are not interesting. So we started to develop with the IVOA the idea of the server-side operations for data access. And so this is an idea that you could do something on the data file and retrieve the result of that action. And this would allow us to go from a person trying to retrieve a megacam frame, which is a 1 gigabyte image, to them really just retrieving a few 1,000 pixels around the thing of interest to them. The amount of people using the service really ramped up a lot, because they would get catalogs, they would download the catalog that we built from the imaging and from the stacks. They would find interesting sources, they would do cutouts, and they would just look at those little cutouts. So the SOTA service became very popular, and it was really a way to get around this 2003 internet bottleneck. And then we built something called the Group Management Service, which helped develop the IVOA's Group Management Service standard, the GMS. So the CFH TLS data and the subsequent CFH large programs, where they had to share data amongst large groups, and they wanted to dynamically add and remove users from it. So we built a method where a project PI could control access to the data by filling in a form and updating the LDAP service at the back end through this GMS protocol. So I heard yesterday that one of the issues is at maintaining these survey lists is like, okay, someone has to email the admin, and the admin can add and remove people from the LDAP listing. Our GMS service basically is just a web interface that allows users to dynamically add and remove groups of individuals from the listing. And we went with this LDAP 389 standard way back in 2005 or 9, or whenever it was, because it allowed something called groups of groups. So you could add a whole group of users just instantaneously to your whole project. Okay, so then as this was evolving, we received funding. Basically, the PI of the Supernova Legacy Survey project realized that the system that they were running couldn't be sustained as an internal compute grid system. And they went to Canary, and they received funding for this CANFAR project. So Chris Pritchett at University of Victoria proposed to build basically the same kind of computing platform that they were running for SNLS, but build it inside Compute Canada's infrastructure as a cloud service. Moving to the cloud was a change, because they had been running as an individual grid. There was a lot of architectural changes that were needed, a lot of work. We went with OpenStack VMs as the approach to doing this. We tried to, as much as possible, have layers that were IVOA standards. When the standards didn't exist for the protocols, we worked with IVOA community to try to develop them. And basically this allowed this, this funded development of a cloud system. We also worked with the HEP group at UVic to build the cloud scheduler, which is a way of orchestrating VMs for cloud computing. And then we used HT Condor as our batch queue system for this initial CANFAR platform. So this is a graphic of kind of what it looks like. We have telescope data coming in on one side, and we have the university research community coming in on the other. And you see this really nice concept, I think, of the data comes into the data center and the users come to the data center. You're bringing the users to the data. You're bringing the compute problem to the data. Currently, this is kind of about the scale that we're looking at. The CANFAR service runs on about 1,000 cores at the Compute Canada cluster. We had thought it would be multi-hosted clustering with multi-cloud, basically, but we haven't really, we implemented it, but we don't find it to be something that the scientists really want to use. They really just use the one cloud. So it's all based on VMs. You can have interactive VMs, or you can have VMs that run in the batch system. Okay, so gone backwards in the slides. And like I said, the service layers between the users and the telescopes and the data center, these are all tried to build these on the IVOA protocols. So we enabled this first generation of the CANFAR system for CFHT and JCMT large programs. And we ran this from 2009 to 2019. I mean, we're still running it today, but the active development of this platform has dropped off quite a bit. It's based, identities are based on X509 certs. We use the GMS system for creating these groups. We have the GMS UI to allow users to maintain their own systems. And the GMS thing actually can work with third-party apps. So we have survey teams using MediaWiki, and the GMS system actually is their authenticator for that. We have storage allocations using the IVOA VO space standard, also controlled by GMS. And I'm just trying to show you the GMS letters there over and over again. This idea of integrating your authentication system into all these different tools in a uniform way is really one of the things that makes this platform really work. It also means you need a super robust way of doing your group management. So, and then we have the, like I said, OpenStack VMs with the Cloud Scheduler and HT Condor. So this is the kind of operational system that we had from 2009 to 2019. Part of that was, let me just back, part of that was that we had users or science teams who would build interactive VMs. They would deploy the X11 windowing system inside their VM, and they would serve that out through a web proxy. And then users would, interact with the desktop through a web browser, and that's how they would do their data analysis in this interactive environment. That was really appealing to the ALMA group here in Victoria, who wanted to be able to do interactive processing, but they needed things like 64-core, 256 gigabyte, or 512 gigabyte RAM machines in order to really process ALMA data effectively. So they needed this capacity, but they only needed it in a bursty kind of way. They didn't need that machine for a year. They needed it for a couple of weeks, and they could give it to somebody else. So the idea was that we could, instead of having individual science teams each deploy their own interactive session thing with their own exact set of software, we would build a generic service, this arcade service, ALMA reduction in the CANFAR data environment. And what arcade does is it uses containers now instead of VMs. And so we have the X11 session or X11 windowing environment in a container. It launches. Then from within the container, you can launch CASA sessions. And there's so many different versions of CASA that you need in order to properly analyze your data. You can basically launch any version of CASA you want as you go along. So, and using containers was really a really robust solution because different versions of CASA have conflicting system level dependencies. And so this allowed us to get around that problem. And so all containers all the time, basically. So containers were a great solution to this problem. This is the architecture of the arcade system taken right out of our final study report sent to ALMA. And really, it's the X11 via no VNC over web proxy and the CASA containers that attach to that display when they run. That was the way to make this work. The thing is, this was all built on top of the service layers that we'd already built for the previous, for the community CANFAR interactive VM. So developing this was actually pretty straightforward. Getting it to work smoothly and to, there's a lot of things we had to learn about containers and Kubernetes and remote storage access that we're still basically scratching out some of the bugs on that. So the service that we built was something that we call SCAHA, which is a tool that allows you to, it talks to a container repository, and then it pulls out your container and it sends it to Kubernetes and runs it as a job for you. Initially, we're using Docker, and then we moved to Kubernetes after that. This is a really excellent way of doing this. And in fact, we immediately extended it beyond just doing the CAS environments. We actually have within that, that X11 desktop environment, a couple of Gemini analysis environments now using IRAF and Gemini's Dragons software platform. This is just basically what this platform looks like. And you can see over here in the pull-down menu, we have a variety of different things you could launch, lots of different versions of CASA. And then there's a little Gemini pull-down for things that you could do with Gemini as well. And here's just someone doing some CASA data analysis in this environment through their web browser. So this worked really well, and we got this all working, and then immediately the scientists said, well, we actually want Jupyter notebooks. And this is actually what we're talking about, this sort of rapid evolution of technology, right? We started in 2003 building the grid engine system, the Sun Grid engine. That ran for 6 years or so, or maybe even a bit longer. Then we moved to using OpenStack and Cloud Scheduler and Batch. We've been running that for a decade. Then we got this desktop environment going for them. And within a year, they were like, well, that's what we want to switch to notebooks. So there's a real churn in how people wanted to do their data analysis. It's actually hard to keep up to. And I could see that the science community on its own, I mean, if they're going to spend all their time focused on this, they're going to lose track of the actual science. So, but the notebooks are great. You can run them in containers. You can contextualize where they run, and you can provide all kinds of different computing capacities inside these notebooks. This is just an architecture diagram, because I know some of you like to see your architecture. So this is basically how the system works inside CANFAR for doing our science portal for these notebook launching. Basically, this is something that might start to be called CANFAR 2.0, where we've gone from provisioning you with VMs and a back-end system to provisioning you with an actual interface. And I liken this to what was mentioned yesterday. Basically, when we built the first CANFAR, we built a Home Depot, and we told our users, you want a chair, go to the Home Depot. And they got there, and they're like, we have to learn all this stuff about how to build VMs and how to schedule them and run them. And my God, this is also complicated. And now what we're doing instead is we're just giving them a chair and saying, just log on to the science portal, and away you go. And I should kind of show you that here. So this is our splash page for the science portal and all of CANFAR. And so the user just clicks on the science portal link down here in the lower right. And off they go. They get this contextualization service come up. I already have a notebook running over here, my AstroPi workspace notebook. But they can contextualize other notebooks with how much memory they need and how many cores they need in that notebook and launch them. You run the notebook. It's the same as any notebook. This is just an example of one of my ones for a class I teach. And the nice thing is, you see here, this is where the notebook assignment for this particular thing is inside of that compute environment. But we're also doing this with VO space, looking at the actual file system storage at the back end. So you can click on the storage management link here, and that takes you to a view of a web view, basically, of all of the files in that compute environment, all served out through VO space. And so you can, students can come in here and they can pull down the assignment, or you can share notebooks with your collaborators. Similarly, you could have these notebooks shared within the actual compute environment. So the first CANFAR was this OpenStack LDAP system for authentication, different OpenStack tenants. The resource management was a little complicated. Science teams were setting up these little mini networks. They were configuring their own virtual machines. Then they were using the Cloud Scheduler to contextualize their instances and provisioning their own little virtual clusters. Then went HT Condor to schedule everything. And then we're using the VO space system, we call it Vault, to distribute data to users and controlling access to that data via the GMS. That's the old CANFAR. And the new CANFAR we have now, this kind of more science portal kind of concept. We're using Harbor, the SCAHA thing we built in Kubernetes to contextualize and launch containers. GMS is everywhere for doing authentication, and it's a nice web interface. We're looking at how to do batch system processing. I liked what I was seeing with the Spark talk earlier. We are also thinking about adopting the cloud scheduler that we actually helped build to run our jobs in batch. And then we're looking at Binder as a possible way to implement some reproducibility. So the design philosophy here all the way has been to be guided by the science problems as they come along. And what is it that someone wants to solve? And we look to solve the general problem rather than the specific issue that the scientist is coming to us with. We have to accept the science users will see this as a general approach as being long to implement, but it will satisfy more users and eventually create a sustainable infrastructure. And so that's a real like a pressure, right, that you have to balance when you're running one of these science platforms, is the specific problem the scientist wants to solve immediately and creating generally supportable, sustainable infrastructure. Wherever possible, we're using IVOA standards to define our API and put that basically on whatever the latest shiny is. And that helps because, you know, we develop standards that are appropriate for the community, and then we have a translation layer onto whatever is the current, you know, best practice in the open source world. And that allows us basically to change that underlying layer as this part evolves, because this, you know, this commercial community evolves very quickly and they provide new services, and we just want to talk to them with our same upper layer all the time. So, hi, so thanks very much for your attention today.
Thanks, JJ. So there are several questions for you. First one from Mario. So is your GMS implementation reusable? That is it possible for someone else to utilize it to integrate SSO on their systems?
Right. So we actually have had an experiment where the GMS is being used by INAF. I don't know if they're using it in a production system or it was just a test system. But yes, it is exportable. And in fact, the idea with INAF was we were actually sharing SSO credentials between the two places. It's if you want to talk more about GMS, just get in touch with us and happy to share.
Okay, there is another question from Mario regarding GMS. Does it allow for authentication via in-common federation? The same system that empowers EduRoam, for instance.
Right. So we actually have, if I go back to the slide here, clunk, clunk. Yeah. If you look here carefully, you can see that we have this little dashed out box here where we are working on the single sign-on through GMS. We currently are using OpenID Connect and that the GMS will use, and we're trying to evolve that basically to EduGain and OrchidID and other identity providers. Haven't quite gotten there yet. Yeah. Okay.
A separate question from Robert. Is your GMS managed by my CADC, or can users create and administrate their own group at will?
Users can create and administer their own groups at will whenever they want. And then they can attach the groups to resources that they have ownership of. And so they can subdivide their resources out into different groups.
Question from Andreas. Can you observe a wider variety of technology preferences demanded now compared to a few years ago? For instance, older people staying with what they know and younger ones excited about new tech.
Yeah, so that, you know, that's a real issue for us to try to stay on top of. We have, I don't know how about the graph here at the very end, but, you know, there was a lot of new technologies that started to show up at the end of this. And when we were we went through a little transition in CANFAR where the science teams that was working with CANFAR, they're like, why aren't you guys using this technology and this technology and this technology? And the number of things they wanted to use basically overwhelmed our capacity to really help them. And now what we're looking at is trying to get more basically research software people and support in the universities and explain to them how to deploy that technology on the CANFAR platform themselves, because we don't have the capacity within the CADC to satisfy this growing diverse set of platforms. Someone came to us just yesterday, in fact, and said, how can I get Pluto, I think it's called Pluto, deployed on CANFAR? And it's like, okay, we'll have a conversation with you because you can deploy it yourself using containerization. And we don't have to understand what Pluto is. You just go ahead and do it.
Okay, another question from Vandana. How are you collecting input from the science community regarding what they want?
So most of the input we get comes rather organically, I would say. We are known within the Canadian astronomy community for providing the CANFAR platform, and they reach out to us directly. We have been co-applicants on a number of funding proposals to build new infrastructure. And so in those proposals, the scientists come to us and they describe their problem and their ideas for a solution. We kind of take that input, try to build a comprehensive solution for them. And we work together basically as collaborators on developing that. Most of the contacts have been coming actually through the Canadian astronomy community with just direct interaction. There's only a few hundred of us, so we all know each other.
Robert has another question. Have you been thinking about concurrent editing of notebooks? So more than one editing a single notebook. Yeah, so one of the features actually that we have is that I could let you interact with my notebook directly just by sharing it with you, the same way you might share a Google Doc. We haven't experimented too much yet to see how that's going to work with basically two people simultaneously accessing the same notebook and perhaps editing it. It is a capacity that exists, but we haven't experimented too much with whether it would work and what the problems are going to be. Okay. And the last question, again from Vandana, have you identified any areas where new IVOA standards are necessary? So we are working with on the GMS side to make that standard sort of come to fruition. And now looking at how we're doing notebook launching, our SCAHA service is talking to Kubernetes, but it could be talking to Docker. It used to talk to Docker. There may be some other container contextualizing system out there that it could talk to. And I wonder if there's a need to sort of say, okay, well, what should be the way that I call a service that will launch a container inside an astronomy data center? I don't care what they're using underneath, that I can call this in a standard way. So I see that as a possible required standard for astronomy inside the science platform. And then there's been some other ones, some other thinking about extending things like how the TAP protocol works, because we also provide table access through this platform. And also how the single sign-on, how we might do single sign-on across different astronomy science platforms. So, okay, thank you very much, JJ, for your presentation. And we will go next to the next talk, so the last of this session, and it is Veronique Valette from the French Space Agency.
Good morning.
Good morning, Veronique. So can you share your screen?
Yes, I will try. Can you see my presentation?
We can see your PowerPoint, but not in full screen.
Yes. And here?
Now it's good. So go ahead, the floor is yours.
It's good. Okay. So good morning, good evening, good night, I don't know. I am Veronique Valette. I'm working in CNES, that is the French Space Agency. And I am head of the office responsible of the development of scientific ground segments. So I will present you today the CNES Computing and Data Center serving scientific projects, the existing and the roadmap. After presenting the CNES scientific projects, including astronomy projects, I will go through the 3 decades, 2010, and presenting to you the CNES Gaia Data Processing Center. And I will present then into 2020 what we do in order to serve the scientific project with the high performance computing, data lake, virtual research environment, data labs. And then I will conclude on presenting the next decade that we are preparing with the large ESA projects, Athena and LISA, where CNES has a large participation in these projects. So here I have some slides on the operational programs, the programs that are now in operations in CNES from 2003 up to 2019, but in the next you will see 2020. So here we have a lot of scientific projects, but what we can note is essentially Gaia in the big data processing of Gaia, and we also participate to the projects with the NASA on the rovers on Mars, Curiosity, InSight, and then this year on Perseverance rover we have the mission center of the French instrument Supercam. Concerning the program that are being prepared or developed by CNES, and in the astronomy field, what I can note in all these projects is the SWOM mission, that is a French-Chinese mission aiming to detect gamma ray burst, and the Euclid mission, that is an ESA mission. I think that everybody knows Euclid mission, that is concerning the dark matter and astronomy. So we are participating a lot in the Euclid science ground segment, as CNES is responsible of the system team of the consortium. We are also working on what we call the scientific challenge, that is the testing of the pipelines, the Euclid pipelines before launch. And we are going to participate also largely in the Euclid operations in cooperation with Italy. And we are also working a lot on to help the French laboratories to develop the codes to develop the codes. And the Euclid we are involved a lot in the Euclid development, but the Euclid data center for France will be in Lyon in IN2P3 and not in CNES. So I will talk to you of something, a project that is running in CNES, is the Gaia Data Processing Center. And the Gaia mission was the first mission, the first big data scientific mission, space scientific mission. And we were, before 2010, we were trying to find a solution to process all the Gaia data. I remind you, 1 billion stars were planned with an average of 80 observations per star. And the story has shown us that it was not 1 billion, but nearly 2 billion stars that have been seen by Gaia. And the CNES was in charge of one of the data processing centers. There are 5 data processing centers for Gaia in Europe. So the challenge was to find a solution, and we have seen very quickly that the classical databases, SQL databases, were not powerful enough to process and to have to take into account all this volumetry that was a petabyte order. 3 petabytes were planned, but in fact it's more than this. So we have done database analysis and study, and we have selected in 2010 the Hadoop solution that was at this time it was really new technology, not used in science project, but used by the Google, Amazon, and Facebook, eBay companies, more than in scientific projects and in the laboratories. So we have put this solution in place, and it has been a it was a really good choice, because we managed to have the main advantage was scalability, and so we can add machines, and there is no bottleneck, as with this sort of Hadoop cluster. We move the code to the data and not the data to the code. So we had a lot of really good performances. Here I show you the technologies that that are now used. We have first of all, we have chosen the Hadoop solution, and then we put up to Hadoop the cascading tools in order to integrate the scientific chains easily, and to put in place the MapReduce paradigm. And then we have also added the Gluster FS solution, as it is for the performance. So the data are stored in a Gluster FS. We have also used Elasticsearch solution with Kibana and Zabbix in order to supervise the cluster and to analyze the logs. And concerning the deployment, Puppet and Foreman are used. And we also use the Fabius orchestrator in order to orchestrate all this processing. Fabius is a CNES tool, specific tool that was used for Earth observation programs, and that has been adapted to Gaia. Just some words about now in 2020. Gaia was launched in 2013, and it was launched for 5 years mission. We had an extension, so we can plan for a 10 years mission. In 2020, we are quite in just after the middle of the mission. So our cluster now, our Hadoop cluster in CNES is I have put here the figures. I will not detail all, but we have now 5,900 cores and nearly 6 petabytes of data of disk. And we plan, and every year we upgrade the cluster in order to manage the obsolescence of the machines and in order to increase the capacity. So it is running really well, and we are now processing the spectroscopy, the solar system objects, the binaries, the galaxies, and the astrophysical parameters for the next release, the Gaia data release number 3, that will be available beginning of next year. And what I can say as an example of the data that is processed in CNES is 3 billion spectra that are processed in order to give the radial velocities of the stars for this data release. It's an example. So after Gaia, what we can notice is that for Gaia, we have chosen a specific solution, and the Gaia cluster is only used for the Gaia project. Now we try to have some solutions that are multi-projects, and in CNES we have not only astronomy projects, but a lot of Earth observation projects concerning French projects or multilateral projects, but also projects with ESA, the Sentinel missions. So we have approximately 10 petabytes of Earth observation data in CNES. So we have put in place CNES. We have a CNES computing center that is now that is more and more user-oriented and service offer. We have the computing platform, the HPC, that is going to grow next year. And here you have the figures: 12,000 cores and nearly 9 petabytes of storage. We have also a storage platform called Data Lake. Currently in development, we have 16 petabytes of tapes, but we are going to extend this this year and next year. Some services and application around this this computing platform and this data software modules specific, GitLab and associated, Jupyter Hub and Pangeo, the container technology, Singularity, and some artificial intelligence, GPUs and Python's software. We have also an important user support and expertise by our engineers that are specialized in scientific computing, big data processing, and artificial intelligence. So that I will just some words. It is the technologies I think are quite used by everybody. We have the same choices. It's so the data around the data lake. We have some functions to ingest and store the data, to diffuse the data to the users, to visualize the data, to analyze the data and put added value to the data, to share the data, selected diffusion, fair data, external data access. What we do especially in the Earth observation projects, we have data from different satellites, different instruments for the same regions and for the same regions and for different timings. So people are really interested in taking this data and analyzing the data and this can produce really added value data. concerning the last thing is the long-term archive, as CNES is the French space agency, and one of the commitments of CNES is to store all the data that comes from the space projects and from the space instruments. So we have a long-term archive. We are committed to store all the data for a long time, and in order not to lose any of the data that comes from the satellites and the instruments. So we have a data lab. I remember the definition of the data lab that we are putting in place. So it is a web workspace giving you transparent access to all component services needed by a user project in order to access, process data, and design for easy collaboration, interaction with a community from the proof of content to the production. The community can be the Earth observation community, the astronomy community, the planetology community, and the community is also concerning Earth observation, some startups and little companies that produce value-added data from the space data. So here I give you I will not detail because I think that I have not the time to detail all this, but it is how we see how we have put in place the data lab. So we have the kernel, the thematic, sub-thematic, and the project layer. And it is linked with the data lake, the processing, HPC processing center, the system tools, the software factory, and the support. And the data lab does not replace the structure of the projects, but it provides a functional and organizational framework. Each project or structure is decision maker and has to use this data lab to take what is useful for the project from the data lab. And we have also Confluence, Jira, some project management tools, and a CNES software factory. I will not detail, but it is a collaborative platform, and that can be shared by the CNES, the partners, the laboratories, and the industry, and that is accessible. It is a lot. There are some tools to improve the development. I will show here all the tools that are put in place and usable by the laboratories, by our developers inside CNES and outside CNES. So there are really the tools that are not. There is GitLab, Jenkins, SonarCube to analyze the code quality, and Jira, and you see here all the software factory, and this is in place since some years and used by a lot of projects and a lot of users. So I will go to the last part of my presentation, preparing the future for us in CNES. The big projects for the next decade and that are going to be launched after 2030 are Athena and LISA. Athena is we work in there are two instruments on the ESA satellite, Athena, German instrument, and the French instrument. The French is XIFU, and we are working on it is really the beginning of the ground segment development, but we are analyzing instrument demonstrator model data, and for this analysis we use all the data lab the CNES facilities, and you will see. The volume is not really important, but the algorithms are very have to be developed, and here I see you. I show you how we use all this to develop the prototype of the Athena test data processing framework. We use all these tools that I have presented, the Jupyter Hub. It is accessed by users, scientists, and developers from outside CNES, and we use the GitLab, the Jenkins, the Jira, and Confluence environments. And this will be the prototype. This is a prototype of the future expertise center for the IFU instrument in operations. Concerning LISA projects, it is the consortium, and the scientific ground segment consortium is under discussion, and there are a lot of things to be done. It's just the beginning of the mission, the phase A of the mission. But what we do now is we use used by the French scientists of the CNES HPC Data Lab for simulations. So French scientists use our the CNES environment in order to run a simulation of data. I remember that LISA is a mission, an ESA mission for gravitational waves. All the consortium uses the CNES Confluence environment also to share documentation and to share information. And the positioning of France, we are positioning France for a data processing center in CNES, using CNES computing and data center facilities that I have presented. There will be, it is not decided now, but there will be a lot of data centers for the processing of LISA data. And the French one is, we propose that the French one will be in CNES. And that's all for my talk. Thank you for your attention.
Thanks, Veronique, for this talk. I don't see any question on the Google Doc, but I have one myself. So can you comment on the benefits of using, I noticed that for data transfer for Gaia, you are using Aspera from IBM. Can you comment on the benefits of using that tool compared to the other open source tools like GridFTP or even HTTP?
Yes, we use Aspera. It's a choice that we have done with ESAC, and I don't know if Will is here, but it was done by with William O'Millan and ESAC at Gaia to exchange the Gaia data, and we have seen really early in the project that FTP was not enough performant, and the Aspera tool was chosen by ESA and not by CNES, because in the Gaia architecture, the ESA is a central point, and they spread all the data to all the data centers. And it was not a CNES choice; it was a Gaia consortium choice. But it was really performant, and we have no problem with Aspera in the data exchanges.
Okay, now we have more questions. So Robert asks half jokingly, what's with the popularity of the data lab word? So first there was the NAOC data lab, then ESA data lab, and now CNES data lab. So can you comment on that?
Yes, I think data lab is a name that is popular, and it's a new data lab. You have also virtual research environment. So yes. Every institution, every data center, data processing center, and agency or laboratory, I think we'll have its data lab.
There is a question from Jorge. I would like to know which Hadoop distribution did you choose?
Just it was 10 years ago. I will just I have forgotten, but I will give the information in the. I will add the information in the slides.
Thanks, Veronique. Last question by Knut. Have you tried your database trade study again more recently with updates to many of the DB technologies over the past 10 years?
The Gaia database study. It's a question.
I guess that's related to the Gaia.
Yes. We have what we have done with our developer was a Spark study in I don't remember 2016 or and we have the results have been published in the BITS Big Data from Space conference. The performances were better at some point with a Spark, but we have chosen not to go to Spark because it would have been too difficult and too much changes in the cluster. But yes, we have studied the Spark technology.
Okay. Thanks, Veronique, again. So this closes this session. So we have now a break.
Fabio, just a quick question.
Announcements.
Yeah, just a quick announcement. I'm going to have to restart Zoom, okay? So I apologize, so please re-enter later on, okay?
Okay, so people have to disconnect and reconnect.
Well, we'll disconnect everybody, but please join back in.
Okay, so we reconvene at 1:30 p.m.
25.
Brasilia time. So that's 27 minutes from now. So see you later.
Okay.